speaker of the day and of the school is Matthew Seiberg, who will continue to tell us about SUSY.
Yeah, I appreciate the fact that, I don't know, I'm worn out, but I'm impressed that you guys are still here, and I appreciate it. So in the first lecture, we talked about SUSY breaking in general, mostly in the context of classical field theory and maybe one-loop corrections. Then we went to part 2, which I'll finish during this talk, which was without SUSY breaking. This is a system which does not break supersymmetry, SUSY QCD. And that was a review of Brian Wecht's lectures, more concise, emphasizing points that some of them he didn't emphasize. And I'm really preparing the ground for the fourth talk, which will be about dynamical supersymmetry breaking. Well, I'll combine all the elements that I discussed and will discuss this lecture to discuss dynamical supersymmetry breaking. So I'll use the non-perturbative effects that I'll be discussing today and put that together in the framework of the first lecture to achieve the final goal. So we discussed SUSY QCD. That's an SUNC gauge theory with NF flavors, very much like ordinary QCD. And we saw that classically it has a very rich moduli space of vacua, which depends on how many flavors and colors we have. We can parameterize it by gauge invariant fields, roughly a meson, which is QQ tilde. There are some indices and transpose. Maybe I should, this is a school, so I should be precise. Q tilde Q transpose. And there were some baryons, which exist, and baryons and antibaryons, which exist only when the number of flavors is large enough. Then we turn on a large mass. And no, first we discussed this theory without flavors at all. We discussed gluino condensation. We discussed the superpotential for S. And we emphasized its limitations. And then we considered the theory with large mass. And we derived a superpotential. And that was basically the low energy scale of the theory once we integrate out the quarks. This is one loop computation, copying the answer for the theory without quarks. This lambda is not inside the determinant. And then we differentiated that with respect to the mass to find the expectation value of the meson, which was dead m, lambda to the 3nc minus an f to the power 1 over nc, 1 over the mass. The mass is a matrix. And we also computed the expectation value of S by differentiating with respect to log lambda. And putting all the coefficients, this is dead m, lambda to the 3nc minus an f to 1 over nc. So that's what we did last time. And now I'm going to continue with that. Any questions so far? Again, about the speed. Should I accelerate or not? No. Should I go slower or not? No. Should I go on and on? No. So once we have this as a function of the sources, it's again the same trick again and again. This is a superpotential as a function of the sources. These are the derivatives with respect to the sources. These are the expectation values of the fields. So we can perform a Legendre transform for one of them, for the other, or for both. And that's actually an illuminating formula, so I'll write it here. So we perform the Legendre transform with respect to little m. So we get W effective, which is a function of the meson field m. And if you just perform the Legendre transform, right, you take the expectation value of m from here And you eliminate m with respect to m. Everything is called m in this story. And again, I include the source explicitly in the Legendre transform. This was in response to a question I was asked yesterday. Some people define the Legendre transform without this term. So this is a very interesting formula. It gives us an effective Lagrangian for the meson field M. And we can set little m to 0, so the theory without masses. And then we get only the first term. And at this point, I'd like to make some comments about that. Comment number 1. This formula, the first expression, without the mass, in fact, also the expression with the mass, can be easily shown to be exact. This is the only thing which is invariant under the symmetries. There's no other expression which is invariant under the symmetries in the problem. And I'm sure Brian did that in more detail. So although, and this is again in response to a question I was asked yesterday, although I really derived all these formulas in the limit that the mass is very large, this formula is actually exact. This is comment number 1. Comment number 2. I emphasized before that the Lagrangian as a function of S has its limitations. S is not a light field. Similarly, for generic number of flavors, particularly larger than the number of colors, I stressed, not yesterday, the day before yesterday, that not all the components of M are independent. Similarly, this thing cannot possibly be a Wilsonian effective Lagrangian. So the derivation so far shows us that this is a 1pi effective Lagrangian. It describes the composite field big M. It allows us to compute expectation values by running the Legendre transform in reverse and derive, for example, this expression. But that should not be viewed as a Lagrangian which describes light particles. In particular, as again I emphasized last time, this expression for the expectation value of big M does not satisfy the condition based on the rank. If the mass M has complete rank, NF, then this is again a matrix of rank NF, while if we write it in terms of the fundamental quarks, like that, it is at most of rank NC. So that shows that this cannot possibly be a mode on the moduli space and so forth. Just for completeness, I'll also perform the Legendre transform as a function of S and get an effective Lagrangian for MNS So again, we see the sources, m and log lambda. This has a piece linear in the source, and the rest is what's the result of the dynamics. And the same comment applies here. This Lagrangian includes the field S, which is not a light field. So therefore, this is not a Wilsonian action. This is just a 1pi action. So now that we understand the massive theory, we'd like to understand the dynamics as we turn off the mass. But before I understand the physics that leads to all these expressions. So this is really funny logic. We first derive the equations. We know all the expectation values. And now we should ask, what's the physics underlying it? When the mass is much bigger than the scale lambda, the physics was gluino condensation. We integrate out the massive quarks. We have a low energy theory, there is gluino condensation, and that leads to all these formulas. The physics that leads to these expressions is totally different when the mass is small. And that's what I'm going to discuss next. Are there any questions?
Well, actually, after your earlier lecture, a student asked me following question. Sometimes, and I wonder what's your comment on it. Sometimes it is said that one PI effective function has to be the same as a Wilsonian effective function if the theory has a mass gap. Is it a wrong statement? Because you're referring to this as this is clearly cannot be Wilsonian, so the only meaning of this effective Lagrangians would be 1 pi.
Yeah, the Wilsonian and the 1 pi are the same. Okay, they differ in two respects. First of all, once they include a field which is not the interpolating field for a massless particle, it cannot possibly be Wilsonian. This is rule number one. So that applies here for S. S is not associated with any light particle, so it cannot possibly be Wilsonian. But somebody could say, well, let's integrate S out using its equation of motion and have something which includes only the light degrees of freedom. Then, is it Wilsonian or not? So even if we have, even if all the fields in our Lagrangian are in one-to-one correspondence with light particles, there is still an important subtlety. The Wilsonian action does not include loops, infrared modes of light particles. It is always thought of as a theory with a cutoff in which we still need to perform quantum mechanics. We still need to perform the functional integral. This is to be contrasted with the 1 pi action, which gives us the full answer. We have done the functional integral. This should be treated classically. Now, these loops, especially loops of massless particles, are often associated with infrared divergences. They are associated with non-analytic behavior in the coupling constants, and I'll have more to say about that later. So when we have a Wilsonian action, there cannot possibly be any non-analytic behavior in the coupling constants. The Wilsonian action is always real analytic in the coupling constants in the theory. This has nothing to do with supersymmetry. This is general field theory. So the Wilsonian action is always real analytic in the coupling constant. The 1 pi action includes massless particles running in the loops, and that could lead to all sorts of infrared divergences and non-analyticity. I used to give an example, but you're kind of from the wrong generation, so this example might not be illuminating. But in the Lagrangian of pions, the same thing is common. Once we write an effective Lagrangian for pions, the effective Lagrangian has a power series in derivatives. Whereas if we compute loops in the effective Lagrangian of pions, we get logarithms of the momenta. Logarithm of the momenta can arise, is non-analytic, and it can arise only from loops of massless particles. Therefore, these logarithms are there in the 1 pi action, but they are not there in the Wilsonian action. This is probably more than you bargained for. I can give a whole lecture about that, but that's not the topic I'd like to emphasize. Any more questions? Are there any other questions that students ask professors and were embarrassed to ask?
Isn't the point there that it's not just whether you integrate over the massless all modes or only the ones that are massless, but also if you include sources with respect to, as you're doing, you write a source with respect to some particular operator, and then do a Legendre transformation and compute the effective action for that. That source, as you're saying, needn't correspond. The dual variable needn't be the field of any one particle in the
Exactly.
any particle.
Exactly. These are precisely the
That's why it's
two.
not Wilsonian.
Yeah. Right. So these are precisely the two distinctions. One is the story with the sources, and the other is the presence of massless particles. So we have to include only modes which are in one-to-one correspondence with the massless particles, or the light modes. Having said that, we'll see that the 1 pi action can be very useful in finding the Wilsonian one, as I'll be doing now. In order to do that, we have to recall what we saw in the classical theory. In the classical theory, we saw that there is a modular space of vacua in equivalent ground states, which was different depending on the number of flavors and colors. So let us discuss now the case when the number of flavors is less than the number of colors. So recall that classically we had a moduli space of vacua which was parametrized by a meson field M. So the classical moduli space was the space of all M's. No constraints, no nothing, just a space of M's. We could ask whether this vacuum degeneracy, the fact that we have a moduli space of vacua, whether this persists in the quantum theory or not. So first we compute radiative corrections, loops. Loops do not lift the degeneracy. So the next thing we ask, can there be any non-perturbative effect that lifts the degeneracy? Well, if there is, we should be able to describe it as a superpotential as a function of M. Unlike the previous discussion, now we are thinking about the Wilsonian action. M is a light field. These are the fields along the moduli space of vacua. So we ask, is there anything at all that we can write down? And it turns out that there is a unique thing. In fact, we've already derived that formula. So the only thing that can happen is that we'll derive something which will be proportional to that beast. Simply because this is the only thing which is invariant under the symmetries of the problem. So we want to find the superpotential as a function of M, which is invariant under the symmetries. And this is the unique thing which is invariant under the symmetries. So either we generate this term or we generate nothing. There's nothing else that can be generated. So the big question is whether somehow the coefficient in front of this is 0 or not. So I'm going to give two arguments that the coefficient is non-zero. First, we've actually already derived that as a 1pi action. The fact that it's the same functional form is not a big surprise. This is the only form which is invariant. But we know that it must be present, and therefore this must be present. This is not the historical way things were discovered, but that also allows us to derive the coefficient. So I'm writing the same expression, but the interpretation is now totally different. The interpretation before was that M was a field, or an operator in the theory. We coupled it to sources. We evaluated the functional integral. We did it in some limit, in the limit which is very far from the limit we are here now, the limit of large masses. We integrated out the fields. There was Gluino condensation. We did Legendre transform and so forth, and we landed on this expression. Now we are in a different limit. The masses are much less than lambda. We use the fact that this is the unique expression which is invariant under the symmetries. Since we found it for big M, we must also find it for little m, except that now it is interpreted as a Wilsonian action. And the two distinctions between Wilsonian and the two characteristics or distinctions between Wilsonian and 1pi that Paul so eloquently explained are now clear. M is a light field. It's a field along the moduli, is the moduli, describes the moduli. And the low energy theory is really free, and this term is there. But what generates it? So I hope that Brian explained that. When NF equals NC minus 1, the SUNC gauge theory is completely Higgsed along the moduli space of vacua. If you remember the expectation values with these rectangular matrices, in this case the gauge symmetry is completely Higgsed. Notice that in this case we don't have a fractional power here. The expression simplifies a lot. And in this case, an explicit instanton computation shows that this term is generated, and in fact its coefficient can be computed. This is a first principle computation, which allows us to derive that this term is indeed present. So this is a very, very straightforward, although a bit painful, computation. which derives the coefficient, shows that this term is indeed present. And now we can reverse the whole logic. Once we prove that this term is present by doing an explicit computation in the gauge theory, we know that this term is here, therefore it must be there. We can run the whole argument in reverse and derive that there must be gluino condensation in the theory without quarks. The way I presented it here, I started by assuming there is gluino condensation with some coefficient, and I derived consequences. In fact, we can run the whole story in reverse, and using the coefficient of this instanton computation to run the whole thing in reverse and derive that there must be gluino condensation in the pure gauge theory. Fortunately, all these things, depending on which order you do, you always land on your feet. And it gives the same answer. In fact, once we derive it for one number of flavors, it's clear that it exists for all other number of flavors, because we can add mass to one of the flavors here, integrate out the massive fields, and derive the same expression for fewer flavors, including the coefficient. But it's instructive to see how it arises explicitly. And when the number of flavors is less than the number of colors, we said that the SUNC gauge theory is Higgs on the moduli space to SUNC minus NF. And I emphasize that the theory then has the light particles are the moduli, parameterized by the matrix M, plus the gluons of the SUNC minus NF. This theory becomes strongly coupled, and again, gaugino condensation comes in, and I don't have time to do the whole thing, and it again gives this expression. The gluino condensation of this gauge group has NC minus NF different values, hence the fractional power here. And once we put all the numbers in, we integrate out the gauge fields, we again land on this expression. So that's nice. It ties everything together. The 1PI agrees with the Wilsonian here. We generate this superpotential. And now we can ask, what's the physics? What are the consequences of this superpotential? In order to find the full physics, we need to understand the Kähler potential. The theory is strongly coupled, and therefore we cannot find the full Kähler potential. The Kähler potential is a complicated function. However, far out along the moduli space, the theory is weakly coupled. If it's weakly coupled, to leading approximation, the Kähler potential is derived from the tree-level answer. So at tree level, the Lagrangian has canonical kinetic terms for the fundamental quarks. We can solve and express it in terms of M, and the answer is that K is approximately twice trace of M dagger M to the 1/2. Up to the 1/2, up to the factor of 2, it actually follows from the symmetries of the problem. The Kähler potential should be a function of M, must be invariant under the symmetries. The only thing is invariant is M dagger M. And on dimensional grounds, it must be a factor of 1/2 because M has dimension 2. There's a trace because the whole thing is traced. But this is again a problem in algebra. Expressed the metric the Kähler potential Q dagger Q in terms of the gauge invariant variable M, and you land on that, take that as an exercise. More mathematically, we have a big space parameterized by Q. We perform the symplectic quotient by imposing the D terms and modding out by the gauge group, and that leads to a metric on the quotient space, which is again a Kähler metric given by that Kähler potential. So now we know the superpotential, we know the Kähler potential, and we can find the potential. And the potential slopes to 0 at infinity. So we started with a theory which has an infinite number of vacua. The degeneracy between them is not lifted in perturbation theory, but non-perturbatively a potential is generated. And the final answer is that the theory doesn't have a ground state. This is what's called a runaway behavior. We can turn on masses and then W is this thing and C minus NF. Doesn't matter, 1 over NC minus NF. I'm not going to copy it again. We turn on masses. But the interpretation now is that the mass, or we are in the limit that the mass is much less than the scale big lambda. We integrate out the mass m. We find the same expectation value we have here, the same formula. And in terms of the potential, we have something like that. So the potential starts sloping down. And if the mass is very small, the term with the mass kicks in at very large fields, leading to NC SUSY vacua at large fields. So everything hangs together, but notice that the physics is totally different. For large mass, we integrated out the quarks. The quarks didn't do anything exciting. The meson field is not too interesting. In fact, the limit of this as the mass is large is that this thing goes to the origin. Everything is where everything is strongly coupled. Whereas if the mass is small, this theory really exists at very large fields. The quarks get very large waves, very far from the strong coupling region, which is here. And this region is weakly coupled, and here we can actually compute everything. We know the superpotential exactly. We know the Kähler potential approximately. We can do the small fluctuations and compute the spectrum. So everything is calculable here. This will be important for us later.
How come you changed the width index from 0 to NC?
I didn't change.
Just by switching on the mass? You would think you would have such
Excellent question. The Witten index of the massive theory must be NC, because when the mass is very big, we can forget about the quarks and their NC ground states. When the mass is small, there should still be NC, and here are exactly these NC ground states. Okay? Ignore comments in the literature that there's another ground state. There isn't another ground state, only NC. What about the massless theory? The massless theory, what happens is we turn off the mass. These guys shoot off to infinity and disappear from the Hilbert space because the potential looks like that. What about the Witten index? The Witten index cannot be computed in the massless theory because of infrared divergences associated with the flat directions. So there isn't really a, okay, if you wish, there's a fine print in the Witten index paper where if the asymptotic behavior of the potential changes, the classical potential, the Witten index can change, and indeed, once we turn off the mass, the asymptotic behavior of the potential changes. Even more so, because of the flat direction, there is a continuum, and the Witten index is not even well defined. So not only can it change, it's not even well defined because of this continuum. So things are consistent.
Why does your potential hit 0 then in your last diagram?
Yes?
Why does it hit 0?
Why is it 0?
Yeah, why is it 0 right here?
Because for supersymmetric ground state, the potential must hit 0. So supersymmetric ground states are characterized by 0 energy. And these.
So the other term we are adding now has.
So if we have only this term, it looks like that.
Yeah.
So this is the non-perturbative superpotential leads to that.
Yeah.
The tree level is just m, proportional to m. Looks like that. If we have both, we don't add the potentials, but we add the superpotentials. We take the derivative and we square it, and that leads to something like that, the white curve. So So it should asymptote to this. My artistic abilities are kind of challenging. Any more questions? When am I supposed to finish? I can't calculate.
Until 11. 11.
Till 11, that's the first lecture.
And then you start again at 11:30.
Okay. I'm sure that Brian said more about that, so I will not elaborate more. But I'd like to move to larger number of flavors because there I think the physics is much more interesting. Here, everything I said about the distinction from, okay, so now I'm changing topic. Well, it's in the same topic, it's the next subsection. And I'm actually going to start with equal. Already for equal, we see that the story cannot remain unchanged. It cannot remain unchanged because, as I said, we have more constraints. Since we have constraints on the moduli space, this cannot be the Wilsonian action. But even more so, let's try and attempt that it would be the Wilsonian action. This thing is not too exciting for NF equals NC. First, the coefficient vanishes. And second, we have 1 over 0 here in the exponent. So if we blindly substitute the value, we see that it doesn't work. In fact, if we go to more flavors, again it doesn't work because, as I said, the rank of the matrix M is constrained to be at most NC on the moduli space, but not for the fields. Recall this distinction. So again, on the moduli space, the rank of the matrix M is constrained, and therefore the determinant vanishes, and therefore this is not too interesting. So this expression, or as I derived it here, for the 1pi action, maybe I should recall that this is the summary of the 1pi. This expression, although very useful and interesting, is fundamentally wrong when NF, for the Wilsonian action, when NF is bigger than NC. So I'll just state the answer for NF equals NC. We said that the classical moduli space had a constraint like that. This was simply the determinant of the quark. This is the determinant of the antiquark. This is the determinant of the quark times the antiquark. So this is just a property of matrices. So this is the moduli space of vacua. Can the degeneracy be lifted? In order for the degeneracy to be lifted, we need to write a superpotential that would lift the degeneracy, that would lead to a potential on that space. But this is the only thing which is invariant under the symmetries. It doesn't make any sense for NF equals NC. And therefore, there is nothing we can write down. And therefore, the degeneracy is not lifted. So unlike the previous case, here the quantum theory also has a moduli space of vacua. Non-perturbative effects do not lift the degeneracy. However, it turns out that the space is modified. So the modular space of quantum vacua is modified, and the right-hand side is non-zero. Let me draw a caricature of this space. The classical space has singularities. So it looks like these two cones. Right? This is a singular space, has a singularity at the origin. This deformation of the space does something like that. So asymptotically very far, when M and B are large, see these two spaces are the same. But near the singularity is smoothed out, and the resulting space is completely smooth. So this space is completely smooth. The singularities here were associated with unbroken gauge symmetry, with massless particles, gluons. Here, there are no new massless particles. The space is completely smooth, and as we move around, there are no new massless particles. So these gluons are gone, and we interpret that as confinement. Just because there were gluons classically, they're not there quantum mechanically.
Last question. Can you get the coefficient in front of the lambda term?
Yep.
How do you do that?
Let me derive it now. Actually, I will only tell you how we derive it. How do we know this is true in general? How do we know this is true? One way to do that is, okay, let me say one more thing and then I'll answer that. There's an effective way of describing this constrained surface. We can write an effective superpotential with a Lagrange multiplier like that. And again, I want to emphasize, this cannot be a Wilsonian action because it includes two fields which are not light. One is the Lagrange multiplier x, and the other is the field describing the constraint. These two fields are massive, as you see here, one times the other, so that's a mass term. But the remaining modes are light. So this superpotential is very useful as long as we don't ask questions about the massive modes. Then we can use it as a Wilsonian action. So I just pulled this field x out of a hat. This is a Lagrange multiplier. It's not really any dynamical variable. But this is something which is extremely useful. One thing we can do with that is turn on masses. So we can turn on our masses. And imagine we turn on only one mass. So this mass has one non-zero entry and everything else is zero. We can integrate out the massive fields and guess which superpotential we'll end on. We'll end on our friend. Knowing the coefficient here determines the coefficient here. So all these coefficients here, all these numbers of order 1 are tied together, and we have all of them under control, and that's why I knew to write 1 here. And again, it depends on the subtraction scheme, and throughout I'm in the dimensional reduction bar scheme. Which is the most common scheme. So I'm kind of planting now various seeds that I will use in the next lecture, where I'll use all these mechanisms, all these dynamical mechanisms to dynamically break supersymmetry. So I'm not giving really a talk about the dynamics of the theory, but only preparing the ground for that, assuming that Brian covered that material. As we go up in the number of flavors, of course, things become even more interesting. Again, when the mass is very large, we've already understood everything. So we are interested in what happens when the mass is small. We've already argued that the vacuum degeneracy cannot be lifted. In fact, this modification of the modular space cannot be present for more flavors, and therefore the singularities should persist. A general rule to remember is that singularities in the modular space are allowed, and they signal the existence of new massless particles. So the question we would like to address is, what are the massless particles at the singularities of the quantum moduli space? Again, we had a classical moduli space. It had singularities. The massless particles at the singularities were the fundamental quarks and gluons, which were not Higgs. In a quantum theory, we have singularities, and the massless particles at the singularities in the quantum theory could be different from the massless particles in the classical theory. So the question we would like to answer is, what are the massless particles at the singularities? So I'm just going to state the answer, because this would be a whole lecture by itself. I should say that. So here we have a dual gauge group. So the massless particles at the singularity are associated with another gauge group, which we'll refer to as a magnetic gauge group. So we'll refer to the original variables as electric. This is this SUN gauge theory. Here we'll have a magnetic gauge group, and the gauge group is SUNF minus NC. And it has NF quarks and antiquarks, not to be confused with the original quarks. These are quarks which are charged under this gauge group. And we have a superpotential, 1 over mu. I'll explain in a second. Let me put all the transposes where they belong. Q trace transpose M Q, where M is now a fundamental field. So the cast of characters are the gluons of this gauge group, the magnetic quarks, and the meson M. So the meson M is now a fundamental field in the dual theory. It turns out that this theory is equivalent to the original one. Classically, they're totally different. They have different number of particles, different gauge group. They have nothing to do with each other classically. Quantum mechanically, they turn out to be the same. And again, this is a subject for the whole lecture, which I'm not going to do. Did Brian explain all that? He did. Okay, so I don't need to do that. I'll just make a few comments, and we'll take it from there. There are various special cases. Okay, so first of all, M has dimension 2 in our conventions, and that's why we put a scale here, mu, to fix the dimensions. Q and Q tilde have dimension 1. This is dimension 2. The superpotential should have dimension 3, so we have 1 over mu. Depending on how many flavors and colors we have, the physics of this duality is somewhat different. Let us start with large number of flavors. So first of all, if the number of flavors is bigger than 3 times the number of colors, the theory is not asymptotically free, so we are not discussing it. Next, let it be between 3/2 NC and 3 NC. Put an equal here. This is the electric theory. Theory. Under renormalization group, the coupling constant starts being bigger and start flowing to the infrared. And at some point, we stop at a non-trivial superconformal field theory. If we are near the end here, this flow is very short because the 1-loop beta function is extremely small, and everything here can be described perturbatively. Otherwise, this is just a strongly coupled field theory. The magnetic theory over there is different. So at short distance, we have a different fixed point. Again, free at short distance, just like this one. It's again asymptotically free. And since it's asymptotically free, as we start flowing to the infrared, the couplings become larger. But it flows to the same non-trivial fixed point. So here the duality is somewhat less surprising. These are simply 2 different Lagrangians which flow to the same fixed point, to the same non-trivial fixed point. This is very common in in 2 dimensions, and now we see it also in 4. So this is the statement of universality. These 2 different gauge theories are in the same universality class. When the number of flavors is less than 3/2 the number of colors, but say bigger than NC plus 1, we can start from the electric theory flow down. But the magnetic gauge group, you can check, is infrared free. It has more flavors than colors, more than 3 times the number of colors. So here, it gives us the infrared behavior. This is the most interesting case. It's the most interesting case because the electric theory is the question, and the magnetic theory is the answer. In QCD, the quarks and the gluons are the question, and the pions are the answer. The question is formulated at short distance, and the long distance physics is the answer, right? That's what we do in physics. We formulate a Lagrangian, you ask, what's the spectrum at long distance? The long distance theory is infrared free, and that means that all the interactions in this theory run to 0 in the infrared. We can really identify these particles as the particles in the spectrum in the infrared. So this is very surprising. We start from a certain gauge theory at short distance, and at long distance, we end up with a gauge theory which is different. The gluons here have nothing to do with the original gluons. The gauge symmetry here is not part of the original gauge symmetry. It came out of nowhere. I like to say that, therefore, gauge symmetry cannot possibly be fundamental because it came out of nowhere. In fact, gauge symmetry is not a symmetry. The Hilbert space is not in representations of a gauge symmetry. But the Hilbert space is always invariant under the gauge symmetry. Gauge symmetry is simply a redundancy in our description of the physics. It's a very convenient redundancy, but as we see here, it's not fundamental. Fundamental theory has one gauge theory, fundamental in the sense of short distance, where we formulate the theory. The electric one is one gauge symmetry. And at long distance, we find a totally different gauge symmetry. The modern term is that it's emergent. This gauge symmetry is emergent.
Can I ask a provocative question? So gauge symmetry isn't fundamental in the same way that general covariance is fundamental.
Exactly. But because general covariance is not a gauge symmetry. But I think that this is much more, yeah. So what was the provocative question?
Well, if one could be emergent, then perhaps.
Well, we know that the other is emergent.
What was the answer?
Sorry?
What was the answer?
Yes.
Are you having in mind ADS CFT?
I'm having in mind even
That's
more
such an
elementary things. I would say the C equals 1 matrix model. The space is emergent.
It's not so good for describing our world, though.
Well, neither is ADS.
Good.
I have a question. Sometimes it is said that in this particular limit which you are considering now, electric theory is more fundamental, and then you obtain a magnetic theory by integrating out some degrees of freedom, and the magnetic theory is less fundamental. Would you say this statement is wrong, that both theories are just exactly the same as the quantum theories?
I don't understand the question. If you define fundamental as what exists at short distance, then yes, the electric is fundamental here and the magnetic is emergent. If you define fundamental in terms of being a fundamental principle of nature, then I would say that either both are fundamental or neither. I can make an example which is much more transparent of that. In 3 dimension, a photon is dual to a scalar field. So the photon has its gauge invariance, the scalar field doesn't. Which one is more fundamental? Well, they're clearly the same. Here is another example. Do electrodynamics, pure Maxwell's theory in 4 dimensions. You can describe it using electric variables or magnetic variables. So either in terms of F or in terms of the dual of F. The gauge symmetry, so you describe it in terms of field strength, and then you write it in terms of the photon, the A mu field. And there are 2 different A mu fields. Electric A mu, such that the electric field F is dA, or the magnetic one, such that dA the magnetic is the dual of F. Which one is more fundamental? Well, they're clearly the same. Where is the gauge symmetry of the magnetic photon in the electric variables? It's not there. In the electric variables, you write the electric photon with its A, delta A is d lambda. And you ask, where is the magnetic photon? Well, it's a non-local transformation and so forth, and this non-local transformation has redundancy, and the redundancy is this magnetic gauge freedom. It's clearly not more fundamental than the electric or less fundamental. The nice thing about these two examples is that these are free theories, so we can actually see the duality transformation. In the more interesting examples, we cannot write an explicit transformation. And therefore, well, I will not even finish the sentence. Yes?
I think you said earlier, you may have confused some people by saying, you said earlier that the two theories are equivalent, but you really meant equivalent in the infrared.
Absolutely.
So, I mean,
So I was if I said incorrectly,
one
I
can be
was
fundamental
wrong.
and the other one need not be. Because one has
If you
freedom than the other.
Right, but if you modify this theory by writing a more complicated Taylor potential, that will be equivalent throughout. As far as the chiral quantities, they are exactly the same because that's determined by the infrared. If you start modifying the Taylor potentials on both sides, you can get complete agreement. Theory energy.
At any energy.
I think so. Well, scalar potential and
But I
high.
mean, if you have a normalization group flow, how can they?
Well, but if you add higher dimension operators, then no. The thing is that once you're in the infrared, you can add high dimension. When I say Kähler potential, I already mean Kähler potential plus higher derivative terms. So, and you can describe the whole thing. It's not a very useful description, but just to show that they're really the same. The chiral quantities are clearly the same. But here we have more than the chiral properties, because that tells us what particles we see in the spectrum. This is very physical. If we just start with the original Lagrangian with the canonical Kähler potential, then at short distance, we see the electric quarks and the gluons. If we do deep inelastic scattering, we see the quarks and the gluons of the electric theory. If we look at long distance, we see these quarks and gluons. These are actual excitations in the Hilbert space. They're very physical.
Possible to express this mu scale without kinemagnetic theory in terms of the
Yes, it is, but it will take me too long to explain. We can absorb it in redefining M so that M will have dimension 1, and then we can absorb it in it. There's another scale here, the scale of this gauge group. And the scale of this gauge group and mu and the scale of the electric theory are tied together. Yeah. And that's explained in more detail in the review I mentioned, when it gives references to the recent literature. Finally, where was I? Finally, we can go to NF equals NC plus 1, in which case we have the magnetic quarks, but we don't have the magnetic gluons because the SU there, SU of 1, doesn't exist. And in this case, just for completeness, I will say that the superpotential is this 1 over mu trace, what did I have there, Q tilde transpose MQ, but we also need to subtract the determinant of M and 1 over mu to a certain power. Doesn't matter. With this, that M that we subtract is again our friend from up there. If you substitute NF equals NC plus 1, you see that we need the determinant. And we'll soon give an interpretation of this determinant. So we need, this is kind of a footnote, that in this particular case, we also have to add this term. Now, let us turn on masses, because everything has to be consistent when we turn on masses and we flow between these different theories. So in the electric variables, we turn on masses by adding mq tilde q. And here, we add trace mm. So I'm going to analyze it two different ways. Both of them will be useful. Way number one, we have a superpotential. Let's look for the stationary points. So we differentiate with respect to m. So we get 1 over mu q tilde transpose plus m. And we are trying to set that to 0. This is a matrix of rank nf. This is a matrix of rank nf minus nc. There is no way to solve the equation. So that looks like supersymmetry might be broken. In fact, near the origin, supersymmetry is indeed broken. However, this analysis is too naive. It's valid when m is near the origin, but there's still all these magnetic gluons, and they could do something interesting. As we turn on the meson m, imagine we turn it on, and we try to ask what happens. As m is turned on, you see that these magnetic quarks acquire a mass. As they acquire a mass, they again can be integrated out. So I'm playing again the same tricks. The magnetic quarks can acquire a mass, very much like the calculation we did before. And when they acquire a mass, we can integrate them out. We are left just with the magnetic gauge group. There is gluino condensation in the magnetic gauge group. Gauge group. And it leads to something which is the determinant of m to some power with some coefficient. Well, there's again only one thing which is invariant under the symmetries. This is our friend from up there. So the full superpotential that is generated is now this term plus this term. And we are exactly where we were before in the in the 1pi action. So let me summarize that again. Ignoring the magnetic gauge dynamics, SUSY is broken. But for non-zero m, q and q twiddle become massive. Because of this term. They can be integrated out. And lambda lambda in the magnetic theory leads to this object. Copying the last term from there, the mass term, we have this effective superpotential. This leads to NC vacua, SUSY vacua, with M, which is the same as there. So we derive the same answer, but now the answer comes from gluino condensation in the magnetic gauge group. You see that in different ranges of parameters, the physics appears to be different. The equations are always the same. All these expressions are exact. But the physical interpretation of these equations and the underlying physical mechanisms vary depending on the parameters. In different ranges of parameters, so when the mass is very big, it comes from gluino condensation in the electric theory. When the mass is very small, it comes from gluino condensation in the magnetic theory. Fortunately, we land on our feet and we get the same answer. I'd like to make one more comment here. The operator M has rank NF. Along the moduli space of vacua, M has smaller rank, NC. In the magnetic variables, all NF square components of M are physical. So here we have more M variables than in the electric theory on the moduli space. And indeed, when we solve for the expectation value, like here, we get the same answer we had here, which has the full rank. So as long as we discuss the moduli space, the rank of M is constrained. But as an operator, the rank of M is arbitrarily large. It could be as large as NF. Now, there's a lot more I can say about that, and I'm sure Brian said more. And more can be found in the review. I'll refer you to that. What I'll do in the next lecture, which is the last one, I'll pick all the pieces that I carefully planted and all these side comments that I had here and there. They will all be important. When we put all the pieces together, we'll use the dynamics that we learned in the last lecture and a half, put it in the context of the first lecture and a half of supersymmetry breaking, and we'll show how supersymmetry can be dynamically broken. So again, so this is important. Let me restate what I said at the beginning of the lectures. We had a hierarchy of hierarchies. We wanted to understand why the weak scale is so much lower than the Planck scale. So in the MSSM, it's the most primitive way of doing it. We have explicit supersymmetry breaking. We put in the terms by hand. In the first and half of the second lecture, we had spontaneous supersymmetry breaking. The Lagrangian was supersymmetric, but the ground state was not, so supersymmetry was spontaneously broken. That stabilizes the hierarchy. Radiative corrections do not ruin it. The symmetry is exact. However, it does not explain where we got the small scale from. With dynamical supersymmetry breaking, we'll explain where we got the low scale from. We get the low scale through this exponential suppression with the coupling. So I think we'll stop for tea now or coffee, and we'll continue in half an hour? Oh, are there any more questions? Any more questions? So if you're embarrassed, you can ask your professors outside, and then they will come.
Yeah, well, one question. I mean,
You should ask your professor outside.
you said earlier that, well, I was going to refer you, that equation you got on the bottom of the board here, you were saying that you could get directly from that because you switched on the masses, and therefore you went from NF greater than NC, or equal to NC, wasn't it, to
Yeah.
NF less than NC, just by making one of them very
Yeah.
massive. And hence that effective potential should reproduce the one
That's right.
previously.
I can
But
also
I was
do-
looking at the two, and but I didn't really see how you do that, because I mean, for example, you've got to get rid of, there's the B and the B tilde that have to
Yeah,
go.
I have to integrate out. So imagine M is some number here. I'll also denote it by m and zeros here. So I have to integrate out this guy. I have to integrate out these guys, b tilde, and x, right? All these need to be integrated out.
X was
The Lagrange multiplier.
Okay.
So all these are massive. So if you want to do the algebra on the blackboard, you integrate out with respect to this one. If you want, I can do it.
Well, maybe I shouldn't subject everybody to a long calculation.
It's not actually very long. Well, a priori, it's clear that you're going to land on the same answer because this has all the symmetries, the other has all the symmetries. There's no other expressions which has all the symmetries, so it must be that. The only thing to check is the coefficient. And if you do this is completely straightforward. You differentiate with respect to all these guys, the equations. You solve the equations, you plug the answer back in, and I can tell you what it will give you. It will give that, let's call it m hat, this thing that we keep. We keep only m hat. So we'll get 1 over that m hat, and here you have m, this m, times lambda was 3nc minus nc, it will be that. You'll end up with exactly this expression. And the 1 over will come from solving the determinant from here, when you solve for the last entry.
So the upshot is that you proved confinement in this theory.
Yes.
Making it the Bruino condensation,
Which
which you
relate-
showed it was passed
Exactly.
by a perturbative effect, well, an instanton
An
calculation.
instanton computation. So
So-
once you do the instanton computation, all the coefficients are determined everywhere. You can also derive that not by going down, as you've just done in the number of flavors. You could also start here and then add a mass and then land on this expression. So you can go up and down in these chains and it all matches, including the coefficients. So I think there's a good chance that this is right.
Any more questions? Okay, let's thank Matthew again.